Good morning class, good morning everyone. In this video, I'm going to share with you or I'm going to explain to you data representation in computers. Okay, so data actually are raw facts. Examples are letters of the alphabet, numbers from 0 to 9, and etc. Okay, so in the computer, data is recorded as electronic signals or indicators. The presence or absence of these signals in a specific circuitry represents data in the computer, just as the presence or absence of punch holes represents data on a punch card. Consider the ordinary light bulb at any given time. The light bulb can either be on or off, or that is, it can be in only one or two possible conditions. It operates in what is termed as binary code. Bi means to the base 2. We refer in two conditions as binary states. Computer components operate in a similar way. A component can be in only one or two possible conditions at any given time. Magnetic materials such as the tiny magnetic cores used in the internal storage units of some computers are magnetized in one direction or in the opposite direction. Transistors are either conducting or non-conducting. Switches are either open or closed. Electrical pulses are either present or absent, and so on. Representing data within the computer is accomplished by assigning a specific value to each binary component or group of components. This technique is illustrated by a very simple 4 light bulb or bulb device in figure 17.1. Assume that the bulbs in the device have been assigned decimal values of 1, 2, 4, and 8. So DC means to the base 10. Okay, when a light bulb is lighted, it represents the value associated with it. When a light bulb is not lighted, it need not be considered. The numeric value representing by this simple device at any time is the sum indicated by the light bulbs. Thus, decimal values from 0 through 15 can be represented by this device. The value of 0 is represented by all lights off, and the values 15 by all lights on. So, in the accompanying illustration, the decimal value 5 is represented because the 4 and 1 lights are on and the 8 and 2 are off. So, in the computer, the values that our designer assigns to the individual binary components become the code for representing data. Okay, so what is binary system? A binary method of notation can be used to describe the setting of binary components. The binary system is the positional numeration system to the base 2. Binary notation uses only two symbols. So, the 0 means off and 1 means on in a specific circuitry. In any positions of the notation, the symbol 0 represents the absence of an assigned value. And the symbol 1 represents the presence of the assigned value. So, Gottfried W. von Leibniz, a 17th century German mathematician, was known to be an advocate of the binary system. Leibniz felt that there was a great beauty analogy between 0 representing the void or empty and 1 representing God or divine nature. Okay, now let us proceed on the table representing decimal data by binary components. So, as explained at the previous slide, okay, this represents actually 5 in decimal. So, meaning you are only going to count the on values. So the on here in a specific circuitry is only the 1 and the 4. See, it's 4 is on and 1 is on in a specific circuitry. So in binary, on means 1, off means 0, or on means presence in a specific circuitry, and 0 means the absence of signals in a specific circuitry. So binary means to the base 2. That's why when you actually observe with this table, this is 1 numbers which are powers of 2. 1 times 2, 2 times 2, 4 times 2, 8, and so on, if the decimal number is actually a large number. Okay, so next. The symbol used in binary notation is 0 and 1 are called bits, which is the short way of saying binary digits. Okay. For example, the binary notation 0101 can be described as having a 1 bit in the 1 bit and 4 bits position. So, and a 0 bit in the 2 bit and 8 bit position. Okay, so any binary number therefore is a sequence of bits or binary digits, possibly with an embedded binary point. Binary numbers that have no fractional part, example given, are without an embedded binary point are called binary integers. The place values in the binary system are the powers of base 2, just as the place value in the decimal system are the powers of 10. So meaning decimal numbers, DC means to the base 10, and binary means to the base 2. So the numbers actually we are using is to the base 10, which is 0 to 9. So computer understands only the 0 and the 1, or 0 means off and 1 is on in specific circuitry. Okay, specifically the place values of the integer part of the binary number are the non-negative powers of 2, and the place values of the fractional part, meaning fraction as part of a whole of a binary numbers, are negative powers of 2. So refers to the table on 17-1 for values of some of the powers of 2. So these are actually the numbers of powers of 2. Okay, so 2 raised to the power 0, actually in mathematics, any numbers raised to the power 0 is equal to 1. You can see the value in binary is 1001 because the first digit on the right side, the value of that is 1. So meaning the second digit is 0, that the value of this is 2, and the third digit is 4, the value of this is, and the value of the fourth digit is 8. So since this is off in a specific circuitry or 0, so this is void, so do not count all of these. That's why this is the value of this is only 1. Okay, next, 2 raised to the power 1. Okay, so that is 2 in decimal. So the numbers we are actually using, or the numbers to the base 10. Okay, so this is 2 in binary because 1 is off. Here, the first digit on the right side is 1 is off, so do not count. The second digit is on, so this is 2. So that's why the value of this is 2, because the second digit is on, and that's the value of that is 2. The third digit is 4, 8 is off, so that's why this is 2. Next, 2 raised to the power 2 is actually 4, and the digit that's actually on here is on the third digit, which is the 4. So 1, 2, 4. 4 is on, so meaning you count this one. So next, 2 raised to the power 3. So that's actually 2 times 2 times 2. That's 8. So 8 in decimal. So this is 0, 0, 0, 1. Meaning the 8 is on. Okay, this is 1, 2, 4. Do not count because those are off in a specific circuitry. So this one is 8 and that is on. And the same explanation with all of these. Okay, so next are the negative powers of 2. So 2 raised to the power negative 1 is actually equal to, in mathematics actually, if negative exponent, you are going to write number above which is 1 or numerator, and then you are going to omit the negative. So this is actually 1 over 2. So 1 over 2 is 1/2, and that's 1/2 is 5/10 in decimal. So this is 5/10 or 1/2 or 0.5. So this is the value in decimal. Next, this is understood to be 1 over 2 raised to the power 2 to omit the negative. So that's actually 1 over 4. So 1 over 4 is that's 0.25 or 1/4, and so on. Same explanation. Okay, this time let us proceed on decimal to binary conversion. So this is actually how computer works. So the computer actually doesn't understand when you press letter F on the keyboard, number 5. So once you press numbers or letters of the alphabet, the computer actually converts it into electronic signals, which is the binary digit or bits, which the computer only understands. So every time you press, for example, a number, the computer converts it into electronic signals. So this is how computer works. So for instance, we are pressing actually 139 on the keyboard. So decimal to binary. How the computer actually works to convert 139 to decimal, or from decimal to binary. Binary which the computer understands. The 0 and the 1, or the on and the off. So this is actually the rule. Suppose that a value expressed as a decimal numeral is to be represented as the binary numeral for storage in the computer. The numeral must then be converted from decimal to binary. Okay, one approach is to use the division multiplication method. The rule is simple. So this is actually the rule to convert decimal to binary. Decimal means to the base 10. Look here, has a sub to the base 10. This is 10, and then the 2. Okay, to convert decimal whole numbers from base 10 to any other base, divide the number repeatedly by the value of the base to which the number is being converted. The division operation is repeated until the quotient becomes 0. So you actually divide the number, the given decimal number, repeatedly by 2, since you are going to convert it into binary. Okay, then stop division only, or stop the division operation if the quotient becomes 0. Look here. Okay, so the remainders written in reverse of the order in which they were obtained from form the new equivalent numeral. So let us take this example. For instance, we are pressing, let us have an actual presentation on how computer works. For instance, you are pressing 139 in the computer. You press 139. So the computer actually converts it into electronic signals. 139, this one. Okay, so this is an example. Repeatedly divide by 2. So 139 divided by 2 is 69. Okay? And you have a remainder because 69 times 2 is only 138. So you have remainder 1 here. Okay, next, you copy the quotient here, then divided by 2. Okay, so 69 divided by 2, that's 34. So, there is a remainder 1 because 34 times 2 is only 68. So, you have a remainder 1. You notice that all remainders are zeros and 1 or off and on in a specific circuitry. So, again, you copy 34 divided by 2, that's 17. So, there's no remainder because 17 times 2 is 34. So, no remainder, meaning 0. Next, you copy 17 here at the bottom, then divided by 2, that's 8. So, 8 times 2 is only 16. So, there is a remainder 1. Next, you copy the 8. Divided by 2, that's 4. And there is no remainder because 4 times 2 is 8. Next, 4 divided by 2 is 2. And there is no remainder because 2 times 2 is 4. Then you copy again the 2 here. Then divided by 2, that's 1. Then there is no remainder. Okay, so the last one, 1 divided by 2 is 0. Remainder 1. So, okay, see, in this portion actually, it's actually constant. It will all stops on 1 divided by 2. And the quotient is 0. And the remainder is 1. So, do not be confused with the last one. Since the rule says you stop the division operation if the quotient becomes 0. So, the quotient here is 0. This time, you stop division. Okay? So, now let us check if this conversion is correct from decimal to binary. Okay? So, you write in reverse from bottom to top, meaning from left to right. You just simply do like this. You write like that. Okay, so here you start with 1, then the 3 zeros, then the 1, the 0, and the 1, 1. See, if we are going to count only the on digit, on means the 1. So since binary has powers of 2, so 1 times 2 is 4, times 2 is 2, times 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, and so on, times 2 times 2, meaning powers of 2. So, if we are going to actually total the on digit, the first digit is 1. Okay? So, let us have an Excel file. And let us check if this is correct. Okay, so let us check if this is correct. So therefore 139 in decimal is equal to 10001011 in binary. Okay, so let us write that one here. So first digit is on here from left to right. Next digit is on 1, off 0, and then on 1, and then 0, 3 zeros, off, and then 1. So, okay, so you count only the on digit. So, let us try to get the sum of the on digit here. So, I'm going to click this one. I'm going to hold down the control in Excel. Click the on digit only, all the on. This one, all the 1. And this one. So we will look at the sum. It's 139 here. So that means 139 in decimal is equal to 10001011 in binary. So that's correct. Okay. So let us have another example here. 25. For instance, this is the given, and you are going asked to convert it into binary here. So decimal to binary. 25 in decimal is equal to blank in binary. Decimal to the base 10, binary to the base 2. So, repeatedly divide 25 divided by 2. So, that's 12. Remainder 1. So, means 12 times 2 is 24 only. So, there's remainder 1. You copy the 12. 12 divided by 2, that's 6. And no remainder. 0. Next, copy number 6. Divided by 2, that's 3. And there's no remainder. 0. Copy the 3. Divided by 2, that's 1. Remainder 1. Okay, then next, copy the 1 divided by 2, that's 0. And remainder 1. Okay, this time no need to write this one because the zeroth or the quotient is already 0. So as the rule says that if the quotient becomes 0 here, you stop division. So now you can write 25 as 1 1 0 0 and then 1. Okay, so let us check if this is correct. 1 is on, so count this one. 1 plus 2 and 4 is off. This one. 2, 4 is off. Next, 8 and 16 is on. This one. So, the 4th digit is 8. The 5th digit is 16. 16 plus 8 is 24. Plus 1, this one. So, that's 25. Okay, so next, another example. Here, 300. 300 divided by 2 is 150. So just if divided by 2, it's actually you just simply think of a number which is half of 300 if you directly divide. So half of 300 is 150, so there is no remainder. So 150 divided by 2, that's 75. 75 times 2 is 150, so there is no remainder. 75 divided by 2, so that's, if 35, that's 70. Okay, let us for instance, 75 divided by 2, it's 3 6 1 15. 15 divided by 2, that's 7 14, remainder 1. So that's 37, remainder 1. Okay, so here you write 37 and the remainder is 1. Okay, so next 37 divided by 2, so that's 16 17 34 18. Okay, 18 times 2 is 36, so 36 daoy sobra isa, remainder 1. Next, 18 divided by 2, that's 9 and there's no remainder. Next, 9, copy the 9 divided by 2, that's 4. So 4 is 8, so remainder 1. Next, 4 divided by 2, so that's 2, no remainder. Next, 2 divided by 2 is 1 and there is no remainder. So we will add another Okay, so copy the 1 divided by 2. That's 0. Remainder 1. Okay, so let us check if this is correct. 300 is actually equal to, copy the 1, 0, 0, 1, 0, 1, 1, 0, 0. Okay, so that's 300. Let us check if that's 300. First digit is off, so do not count. 0, 0, so 1 and 2 is off. 4 and 8 is on. 1, 1, so on. Let us make a red mark for on digit. Next, 16 is off, so no count. Next, 32, count the 32, this one digit. Next, 64 and 128 is off, this one are off. And next, 256 is on. So we will count 256 plus 32 plus 8 plus 4. So okay, let us try to total this one. 256 plus 32 plus 8 plus 4. So these are the on digit. So let us highlight this one in Excel. So that's 300. See the sum. So meaning this is the correct value or the equivalent in binary. Okay, so let us have another example for decimal to binary conversion. Okay, this one. So 9. For instance, you're going to convert 9 into binary. Okay, so the actual of this, the computer, when you press 9 on the keyboard, actually, the computer converts into electronic signals, which is the binary or the 0 and 1. So, okay, so 9 divided by 2, that's 4. Duha ka 4, it's 8, so remainder 1. Next, you copy the 4 divided by 2, so that's 2. No remainder, that's 0. So next, you copy the 2 divided by 2, that's 1. So there is no remainder, 0. Next, you copy the 1 divided by 2, always that's 0, remainder 1. Oh no, 1. Okay, so just erase this one. Okay, so just simply write here 9 in decimal is equal to 1001. Okay, so meaning the first digit is on, so you count the 1. Second and fourth digit is off, so the fourth digit here is 1, meaning on in a specific circuitry. So this is red. So you count only the on digit. 1 plus 8 is equal to 9. Okay, so that's all how to convert decimal to binary in computer. So the next lesson actually is you are going to convert in reverse. If the given is binary and you're going to convert it into decimal, it's actually very simple. You just only count the on digit. Okay, so that's all for today. Thanks for watching.